Welcome to Math TV with Professor V. In this video, we're going to learn about Gaussian elimination and Gauss-Jordan elimination. This is the video lecture for section 1.2 on linear algebra. Definition: if m and n are positive integers, then an m by n matrix is a rectangular array of numbers of the following form. So here I have an example of a matrix. M by n tells you the size of the matrix. And notice here we have m rows, and the number of rows is indicated by the first entry in the subscripts here, okay, which row that entry belongs to. And then it has n columns. That's indicated by the second number that's in the subscript of each of the entries, okay? So things to keep in mind, and that won't change. So m always refers to the number of rows in a matrix, and then n refers to the number of columns. So each entry in the matrix we refer to as A with subscript ij. So ij, those subscripts help you identify where in the matrix that entry is. I is the number of the row, like I just explained earlier. That's the first part of the subscript. And then j is the number of the column, the second number of the subscript, okay? And the rows of a matrix are the numbers that appear next to each other horizontally. I think we're pretty comfortable with how rows work. Again, m is the number of rows. The columns of a matrix are the numbers that appear next to each other vertically this way. We should all have that down by now. So n is the number of columns. And a matrix with m rows and n columns is of size m by n. So that's how we would describe the size of a matrix. Now when m is equal to n, so when you have the same number of rows and columns, then you have a square matrix, and we call it of order n. And the entries A11, A22, A33, up to ANN are the main diagonal entries. So if you have the same number of rows and columns, then these are your main diagonal entries in that square matrix. Okay. One common use of matrices is to represent linear systems of equations. And the matrix derived from the coefficients and the constant terms of a system of linear equations is the augmented matrix of the system. The matrix containing only the coefficients of the system is the coefficient matrix of the system. So look how efficiently we've named things. So write the system as an augmented matrix. You're going to like this so much better than the last lesson that we did, because you're not going to have to write out each of the variables anymore. You're just going to write the coefficient that is in front of each of the corresponding variables. So let's look here at this system of equations. Notice we have 3 equations and 3 variables, and they want us to write an augmented matrix. Okay, first I'm going to write out what the coefficient matrix is, just so you guys can see the difference. Okay, so the coefficient matrix would basically only include the left-hand side of all of the equations in the system of equations. So you would list the coefficients for x1, x2, and x3 in each of the respective columns. So x1, the coefficients are 3 from the first equation, 1 from the second equation, and then 2 from the third equation. Coefficients of x2 would come next, 1, 0, 2, and then x3, -2, -3, 1. So this is the coefficient matrix, because I'm only including the left-hand side of the equations in the system of equations. And notice this coefficient matrix, if we were to identify its size, it's a 3 by 3 matrix. It's a square matrix, okay? But that's not what they asked for. We got to follow directions in math. They wanted the augmented matrix. So the only difference is now we're going to include the constants that are on the right-hand side of the system of equations right here, okay? Augmented matrix. Now you don't put equal signs in a matrix. So what you do is you're just going to draw a vertical line to indicate that the coefficient matrix ends, and then the constants are going to appear. So you still have this Same coefficient matrix, 3, 1, 2, 1, 0, 2, negative 2, negative 3, 1. You draw a vertical line to indicate that's where the equal sign was, basically. And then here's 5, negative 2, 4. So including these constants right here, that's what makes an augmented matrix. Okay, so these are the constants from the right-hand side. And then right here, this is our coefficient matrix from earlier. Okay, very good. Now, what we want to do is manipulate these matrices in order to help us solve these linear systems of equations. And how are we allowed to manipulate them? Well, there's certain elementary row operations that we are allowed to perform. Okay, just like when you were first studying how to solve equations back in the day in algebra class, and you learned you can add a number to both sides of an equation, it will preserve the equality, you can subtract a number, etc. You learned what rules or what operations you were allowed to perform to solve an equation. Same thing here, there's certain procedures that you're allowed to perform on a matrix, okay, that will produce a new augmented matrix that corresponds to an equivalent system of linear equations. So basically, you will not be altering the solution set, okay, the solution to the system of equations. And we say that two matrices are row equivalent when one can be obtained from the other by a finite sequence of elementary row operations. So here are the allowable elementary row operations. You'll recognize them from the previous lesson. First one is you can interchange any two rows. Second one is you can multiply a row by a non-zero constant. And the last one is you can add a multiple of a row to another row. All right, that's it. You don't get to invent anymore, okay? These are the three. Don't go wild. So we're gonna focus on rewriting matrices in two different forms, row echelon form and then reduced row echelon form. Okay, row echelon form is what we looked at a little bit earlier when we performed Gaussian elimination. Okay, and then reduced row echelon form comes from performing Gauss-Jordan elimination. I know. So here's how you're going to remember the difference, okay? Either you just have no problem remembering things, which is cool, good for you. What I think is row echelon form, okay, that has less words than reduced row echelon form. So that matches up with just Gaussian elimination, only one word in the title, Gaussian. And then reduced row echelon form, that has more words, right? Reduced is that extra word. So then you got to have an extra word here, Gauss-Jordan elimination. Okay, if that was lame and you hate it, that's fine. Okay, but it works for me. So anyways, how do we recognize these forms? What is the goal? Well, a matrix in row echelon form, Gaussian elimination, has the properties below. So any rows consisting entirely of zeros occur at the bottom of the matrix. For each row that does not consist entirely of zeros, the first non-zero entry is a 1, okay, called a leading one. And for two successive non-zero rows, the leading one in the higher row is farther to the left than the leading one in the lower row. I know that sounds awful. If I just show you an example, it won't be so bad. So say we had a 3 by 3 matrix and we used Gaussian elimination, meaning it's in row echelon form, okay? Then this is what it would look like. I'm just saying if you had a 3 by 3 and then the augmented matrix would be a 3 by 4, then you would have a 1 up here. You would have to have zeros beneath that 1. Then you would have some entry here. We don't care what it is, okay? And then beneath that would be a 1. And then beneath that would be a 0. And then up here, A13, I don't care what it is. A23, we don't care what it is. And then here's a 1. And then the constants, we don't care what they are. B1, B2, B3. So notice what's kind of going on. So if you look at a row, the non-zero entry has to be on the left, furthest left, and it has to be a 1. And then you have to have zeros beneath it. So then now like turn your attention to this row. First non-zero entry is all the way on the left, and there's zeros beneath it. And then again, look at this third row. First non-zero entry is all the way on the left, and it's a 1. You don't care about what's above it though when you're just getting a matrix in row echelon form, okay? That's pretty much what we did in the last section, just not using a matrix. We still wrote out all the variables, which was obnoxious if you ask me. Okay, now what's this other form and this other kind of elimination? Well, that's reduced row echelon form. I will abbreviate it, RREF. I didn't make that up. That's using Gauss-Jordan elimination. The process isn't any different of the elimination, so don't fret. And in this case, every column that has a leading 1 has zeros in every position above and below. So basically, it's fully diagonalized. So here's what it would look like if you took that same matrix, a 3 by 3, and used Gauss-Jordan elimination. So you put it in reduced row echelon form. Okay, then it would look like this: 1 0 0 0 1 0 0 0 1, boop, and then you have B1, B2, B3, like that. Okay, and this is when we say like you fully have diagonalized your matrix. The reason why it's so nice is, if you remember, since this represents a system of equations, it would be equivalent to saying, for example, x1, 1x1 equals b1, 1x2 equals b2, and 1x3 equals b3. So the nice thing is you can see what the solution is to your system of equations by just looking at this column here when you have put your matrix in reduced row echelon form. Okay, so here we go. The only reason I'm trying to help you remember which form goes with which name is so that when you read the directions on your homework or an exam, you don't get jumbled up, okay? So here we go. Let's look at an example. It's going to be similar to the row operations from the previous video, but nicer because we're not going to be writing out the variables. This is going to be more fun if you didn't have enough fun in the last video. So we're going to solve the system using Gauss-Jordan elimination. So we're going to fully diagonalize this sucker, put it in reduced row echelon form. Love it. So first I'm going to write out the augmented matrix. 3 1 2 1 0 2 -2 -3 1, and then 5 -2 4. Okay, you guys, I personally, back in the day, over 20 years ago, struggled with this process because I was absent the day we learned it in school, and then I was forever traumatized. So it's not as hard as it might look, but you do have to follow the process obediently. Otherwise, you're going to undo the work that you just did to get it diagonalized, okay? So here's how you got to start. Make this entry a 1 first. Okay, you have a couple options for how to do that. You might be tempted to say, I'm just going to take 1/3 times row 1 and make it the new row 1. And you totally could, okay? However, like I'm looking at these entries here, they're not divisible by 3, so I'm not going to love having all these fractions so early in the game. Sometimes you can't help it, you know? But I'm looking and oh my goodness, there's this little 1 hanging out, just minding its own business in the second row. I wish it was in the first row. Well, I'm going to put it there. So what I'm going to do is actually interchange row 1 and row 2. And the way you indicate that you're doing that is you say, I'm switching, put that double arrow right there, row 1 and row 2. Oh, nice. Now we're going to have a 1. Yeah, 1, 0, -3, -2 in the top left. And I didn't have to start using any fractions just yet, so that's good. It'll happen probably for every problem, but if we can avoid it, great. Okay, now that we've successfully created a 1 here in the top left row, top left entry, sometimes we refer to that as the pivot. So you use that pivot to zero out all of the entries in that same column. So what does that mean? I want to make this 3 a 0, and I also want to make this 2 a 0. And you do it using the 1 in row 1. You're going to use row operation number 3, where you add a multiple of that first row to another row and replace it. You can't do it differently. So you only can multiply the pivot row by some non-zero number. So for example, I'm going to take -3 times row 1. Add it to row 2. You can't multiply row 2 by anything because that's going to be the row that you replace. That's going to be the new row 2. Notice I use a capital letter to show that this is going to be the new row 2, okay? The constant gets multiplied by the row that's being added to the other row that's getting replaced, not the other way around. Okay, and then similarly, let's just plan how we're going to make this 2 a 0. You would take -2 times row 1 plus row 3, and that's your new row 3. Okay, now usually I do these all in my head, but if you want, we can just work through a little bit by hand right now for you to see. So if you take -3 times row 1, so I'm going to take -3 times row 1, it would be, let's see here, -3, 0, 9, 6. I'm going to add it to row 2, 3, 1, -2, 5. Add them, and then that's my new row 2, right? So 0, 1, 7, 11. Go get your Slurpee. Okay, that's my new row 2. Row 1's not changing, so let me rewrite it. 1, 0, -3, -2, 0, 1, 7, 11. And then let's do this operation here. I'll do it again in a different color. So -2 times row 1. We're using this row 1. So -2, 0, 6, 4. Add it to row 3, which is 2, 2, 1, 4. Add that up, and that's your new row 3. 0, 2, 7, 8. Okay, here we go. 0, 2, 7, 8. All right, beautiful. So now basically you work from left to right on each column. Focus on each column. So look at our lovely column 1, 1, 0, 0, beautiful. Now you move your attention to the next column. You create your pivot first, or what this textbook calls it is the leading one, this guy right here. Oh, look, we already have a 1 there. I don't have to do a single thing. Fabulous. Now I'm going to use this entry here, this is the pivot, to zero out all of the entries in the column that it's in. So again, life is so nice. We already have a 0 here, so the only thing I need to worry about is making the 2 beneath it a 0. Okay, so how are we going to do that? Use row operation 3. I'm going to take -2 times row 2, add it to row 3, and that's my new row 3. Very good. Okay, what I like to do, notice we're just going to make a new row 3. Row 1 and 2 aren't changing, so I'm just going to rewrite them now so I don't get carried away, you know. This is all about focusing, because if you just make one little arithmetic error, it'll get all messed up. So don't have television on in the background. Don't do any foolishness. Really focus. Silly mistakes are still mistakes. It's not okay. All right. Oh, it's the new row 3. Why did I write row 3? See, look at, I'm getting distracted. Shame on me. So this is 0, 1, 7, 11. Okay, shall we do scratch work one more time? Do you need it? -2 times row 2. So it would be 0, -2, -14, -22, plus row 3, 0, 2, 7, 8. That's going to be my new row 3. So 0, 0, -7, 22 minus 8, -14. Okay, so here's my new row 3, 0, 0, -7, -14. Okay, so look, we're doing so well. Column 1, done. Column 2, also done. Move on to column 3. This -7 needs to be a 1. How shall we do that? Well, let's just take that row and multiply by -1/7. and that will be my new row 3. All right, so here we go. Row 1 and 2 are not changing. So 1, 0, negative 3, negative 2, 0, 1, 7, 11, 0, 0, 1, 2. So here's where I want you to notice something. You might be so tempted, like, oh, I know I'm going to want a 0 here later, and I'm tempted to add these together. No, don't do it, okay? You're just going to end up making a mess of things and undoing stuff that you're going to try to fix later. You got to make this entry here, this a leading one. You have to create your pivot first. Don't start zeroing out things. Okay. So now we've got the 1. I'm going to use this pivot to make a 0 in the column that it lives in, column 3, for all the entries above. Let's do it. So here we go. The 1 is going to be used to make the 7 and the negative 3 a 0. Let's try doing both these at the same time mentally. Yes. Okay, so for row 1, I would take 3 times row 3, add it to row 1. That's my new row 1. And negative 7 times row 3 plus row 2 would be our new row 2. Okay, so the only row that's not changing is row 3. So we've got 0, 0, 1, 2. Okay, here we go. 3 times row 3. So I'm just doing this in my head. See, this isn't going to change anything. 3 times this plus row 1. 3 times this plus row 1. 3 times this plus row 1. Now we have a 0. That's why you have to do it in this order, okay? I'm not being bossy just to be bossy. And then 3 times 2, that's 6, plus negative 2, 4. And then negative 7, row 3 plus row 2. Okay, great. So negative 7, notice this isn't going to change, this isn't going to change, this is a 0. Now the only time I have to think is negative 7 times 2, that's negative 14, plus 11, that's negative 3. Oh my goodness, what a work of art. Here is our matrix, fully diagonalized, reduced row echelon form. It is a thing of beauty. And then now, look how lovely. The first row tells me x1 is equal to 4. x2 is equal to negative 3. And x3 is equal to 2. So if you were to write out the solution set as an ordered triple, x1, x2, x3, it would have the coordinates 4, negative 3, 2. All right, so good. Let's look at another example. They're definitely going to get spicier, okay? So here, example B, we have the following system, and I want you to notice something. Yes, things are getting advanced quickly. We only have 2 equations and 4 variables. And we talked about earlier in the last section, that means we either have no solution or infinitely many, but we will not have one unique solution, okay? So still the same process, it's just not gonna look so nice. You won't get this like cute diagonalized square looking matrix, you know? 2, 6, negative 7, 10, 11, 3, 9, negative 5, negative 8, 30. Okay, same process holds though. So this 2 needs to become a 1. So best way to go about doing that, I can't swap the rows like I did last time, so we'll just do 1/2 row 1 is the new row 1. Okay, so this will be 1, 3, negative 7/2, 5, 11/2, and then let's leave row 2 as is. Okay. And then from here now, remember you have to use that pivot, use that leading one to zero out the column that it's in. So that 3 needs to be a 0. So what would I have to do with row 1? Yeah, multiply by negative 3, then add it to row 2. That's my new row 2. So row 1's not going to change. Row 1 is 1, 3, negative 7/2, 5, 11/2. And then my new row 2, we can do this in our head. So negative 3 plus 3 is 0. Negative 9 plus 9 is also 0. Negative 21 over 2. Oh, but I'm multiplying by negative. So positive 21 over 2. Let me write this out for you guys. Okay. So negative 3 row 1 would be negative 3, negative 9, positive 21 over 2, negative 15, and negative 33 over 2. And we're going to add that to row 2. 3, 9, negative 5, negative 8, 30. And that's my new row 2. So we'll have 0, 0. 21 over 2 minus 5 is 10 over 2. This will be 11 over 2. This is negative 23. Negative 33 over 2 plus 60 over 2 is 27 over 2. Okay, so there's my new row 2. Yeah, that was a dangerous one. And 27 over 2. Beautiful. Okay, good. Now, I'm not worried. It's kind of strange, I know. I'm not really worried about this column, okay? Because this entry here is also a 0. So remember, the first non-zero entry that's all the way on the left, that's what needs to be a 1. So we're gonna really just like skip over this column because this is already a 0, and my focus now is to make this 11 over 2 a 1. So when you look at each row, the furthest left entry that's not a 0 needs to be a 1. So which one's furthest left that's not a 0? This guy, this needs to be a 1. Make sense? How do we make 11 over 2 a 1? We multiply by 2 over 11. So what we're going to do is take 2 over 11 times row 2. That's our new row 2. All right. So we've got 1, 3, negative 7 halves, 5, 11 halves. And then this will stay 0, 0. This is a 1. 2 over 11 times negative 23, that would be negative 46 over 11. And then 2 over 11 times 27 over 2 would be 27 over 11. You know, I know the numbers are not as nice as the last problem, but you're in linear algebra, so just suck it up. Okay, good. So let's look at our progress thus far. This is lovely. Don't pay attention to the second column. Now we've created our pivot, our leading 1, and this needs to be a 0. How am I going to do it? Using row operation 3, you're going to take positive 7 over 2, excuse me. Positive 7 over 2 times row 2, add it to row 1, that's my new row 1. Okay, this might be somewhat of a fractional nightmare, so let us definitely let's write it out off to the side. Okay, so we need 7 halves row 2. That would be 0, 0, 7 halves. Negative 46 over 11 times 7 over 2 would be negative 23 times 7 over 11. 23 times 7 is going to be 140 plus 21. Okay, negative 161 over 11. And then 5 times 7, no, I'm doing row 2, excuse me. 27 over 11 times 7 over 2. Nothing's going to cancel, huh? No. So that's just going to be 27 times 7. So 20 times 7 is 140. Plus 7 times 7, 49. So that's 189 over 22. Okay. And we're adding that to row 1. 1, 3, negative 7 halves, 5, and 11 halves. Yes? We made it. Okay, that's the new row 1. 1, 3, 0. Negative 161 over 11 plus, that would be 55 over 11. So negative 106 over 11. And then 189 over 22 plus, that would be, I'd have to multiply that by 11. I feel like I missed a negative somewhere, didn't I? No, I didn't miss anything. I forgot. I reduced it. Okay, so 189 over 22 plus 11 over 2. After you reduce it, you have 155 over 11. Okay, good. So that's the new row 1. Oh my goodness. Okay. 1, 3, 0, negative 106 over 11, 155 over 11, and then row 2, 0, 0, 1, negative 46 over 11, and 27 over 11. Okay, this doesn't look nearly as cute as our last result, but our job is done. The first non-zero entry in each row, furthest left, is a 1, and there's zeros in that entire column, and there's nothing else to do. Okay, I know, so gross looking. So now how do we write out the solution set? We'll go back to the system of equations that this matrix represents. Okay, so row 1 would be x1 plus 3x2 minus 106 over 11 x4 equals 155 over 11. And then the second row would be x3 minus 46 over 11 x4 equals 27 over 11. And then remember, you just always isolate or solve for the variable that's furthest left. Okay, so here's the system. So x1 is negative 3x2 plus 106 over 11 x4 plus 155 over 11. And then x3 is 46 over 11 x4 plus 27 over 11. So what are the free variables? x2 and x4. Okay, so we're going to have our ordered quadruplet, dare I say, x1, x2, x3, x4. Okay, so coordinates for x1, or x1 is equal to negative 3x2 plus 106 over 11 x4 plus 155 over 11. x2 is a free variable. x3 is 46 over 11 x4 plus 27 over 11, and then x4 is another free variable. So notice here we're going to have infinitely many solutions, yes? Okay, see, we survived. It wasn't the end of the world. Okay, so now some terminology that if you've studied a little bit of differential equations might be familiar actually. We say that systems of linear equations in which each of the constant terms, the ones on the right-hand side, is 0, these systems are called homogeneous. And a homogeneous system must have at least one solution. So a homogeneous system of equations in variables has the following form. So you would write out your system, A11, A12, etc., up to AMN. Those are all the coefficients. But notice here, all of the constants are 0. Okay? So just a little example to kind of play around. Assume A, right here, this matrix, is the augmented matrix of a system of linear equations. Then find the value of K such that the system is consistent. Okay, we'll get back to doing this process with homogeneous systems in just a minute. Okay, but first let's just look at this a little bit more basic example. So they want us to find the value or values of K such that the system is consistent. Remember, a consistent system has at least one solution. It could also have infinitely many. Okay, so let's think about this. This is the augmented matrix. So basically they just didn't write out that line right there, but it represents a system of two equations, two variables. So we've got 1k2, negative 3, 4, 1. And let's just try to start diagonalizing it and see what happens, okay? So we already have a 1 here, hooray. What we would want to do to solve is make that negative 3 is 0. So you would do that by taking 3 times row 1 plus row 2, and that's your new row 2, right? Okay, so 3 times row 1, 3 row 1 would be 3k6, adding it to row 2, which is negative 3, 4, 1, gives us the new row 2, so 0, 3k plus 4, and 7. That's literally what you're going to have for row 2. So 1k2, 0, 3k plus 4, 7. Boop. Okay, what would make us worried, or what would create a scenario where we have an inconsistent system, what we don't want? Well, if you'll remember from the previous lesson, if you have a false statement arise, then the system is inconsistent. And a false statement would come from 3k plus 4 not equaling, or 3k plus 4 equaling 0, right? So we basically don't want 3k plus 4 to equal 0, because then the system is inconsistent. If it's anything else, then we can find a solution. One solution or infinitely many. So we're trying to find what k can be so that the system's consistent. Well, anything as long as 3k plus 4 isn't 0. So we're going to require 3k plus 4 to not equal 0, which means k cannot equal negative 4/3. But any other number is fine. Okay? So again, if k was equal to negative 4/3, so what's the problem? If k equals negative 4/3, we answered the question. I just want to explain it a little bit further in case it's not clear. If k was equal to negative 4/3, then that second equation in the matrix would be 0x plus 0y, assuming it's an x and y, whatever, equals 7. So you would basically have 0 equals 7, right? Which is false. That would make the system have no solution and be inconsistent. Make sense? Oh, good. I'm so glad. So let's look at one more example, and we're going to incorporate that new definition for a homogeneous system as well. So assume A is the coefficient matrix of a homogeneous system of linear equations. Okay, so this is just the coefficient matrix this time. So what does that tell me? That all of the equations are equal to 0, okay? And find the value of k such that the system is consistent. So we want at least one solution. So let's write out the matrix, the augmented matrix this time, because this is just the coefficient matrix, right? And then we'll do a similar process. So since they told me it's a homogeneous system of equations, then I know that the column furthest right is just going to be 2 zeros, like that. And then we have negative 3, 4, 1. Okay. All right, so what we're going to try to do is still put this matrix in reduced row echelon form, and then that way we can better identify the nature of the solutions and decide what k would have to be so that the system will be consistent. All right, so we already have our pivot in the top left. This is already a 1, so I'm going to use that to make this negative 3 a 0. And hopefully by now you're getting the hang of these row operations. I'm going to take 3 times row 1, add it to row 2, and that will be my new row 2. So row 1's not changing. Let's just rewrite it. We've got 1, k, 2, 0. And then 3 times row 1, 3 times 1 plus negative 3, 0. 3 times k plus 4, just 3k plus 4. 3 times 2 plus 1, 7, and this stays 0. All right. Now, next step in the process, we move our attention to this entry right here in the matrix, in the next row. that needs to be a 1. Well, typically, whatever constant is in that entry, you would divide by it, right, in order to make it a 1. So for example, if there was a 5 sitting there, I would divide by 5 and multiply by 1/5 to make that our new pivot. However, I have to be careful. I can't divide by 3k plus 4 if it's 0. So I'm going to assume it's not, so I can continue the process. So I'm going to assume that 3k plus 4 is not equal to 0, in which case now I am going to be allowed to multiply row 2 by 1 over 3k plus 4, and that will be my new row 2. All right, and then I'm trying to create my new pivot. Okay, so let's see what we're gonna have here. Row 1's not changing, so let's just rewrite it. 1k 2 0, and then 0 1 7 over 3k plus 4, and then we still have a 0 there. All right, good. What's the next step? Well, now that we've made our pivot down here, we want to use it to zero out all of the entries in that column, in the second column. So I want to make this k a 0. So how would we do it? Take a constant, multiply by row 2, add it to row 1. So I'm going to take negative k times row 2, add it to row 1, and that will be my new row 1. All right, so row 2 is not changing. 0 1 7 over 3k plus 4 0. That's all the same. Great. And then this one will stay as is. And then we can probably do this in our head, or maybe not. Let's see. So we have negative k. Yeah, let's write it all out. So some scratch work off to the side. I'll do it here. Negative k times row 2 would be 0, negative k, negative 7k over 3k plus 4, and 0. I'm going to add it to row 1, which is 1k 2 0. All right, let's add these up. So this is 1 0. Okay, in order to add these two terms, we need a common denominator. So we have negative 7k over 3k plus 4, plus, if I get a common denominator for 2, it would be 6k plus 8 over 3k plus 4, and then now adding these together, negative 7k plus 6k would be negative k plus 8 over 3k plus 4. So that goes right there, and then this is still 0. Okay, so I have row 1 now, ready to go. 1 0 negative k plus 8 over 3k plus 4, and 0. Okay, I know it's not the prettiest looking matrix on the street, but here we go. It's in reduced row echelon form. All right, so from here, let's go back now that our matrix is in reduced row echelon form and write out the system of equations that corresponds with the matrix. So for the first row, we would have x plus 0y plus negative k plus 8 over 3k plus 4, that's the coefficient on z, equals 0. And then I could solve for x here if I move this term to the other side of the equation. And so remember, if I were to subtract it over, you would just change the signs of the terms in the numerator, right? If you multiply the whole term by negative 1. So x would equal k minus 8 over 3k plus 4z. Okay, so that's what we have for x. And then let's see for, I want a nicer box. I'm so very proud of this right here. Okay, second equation, there's no x, so y plus 7 over 3k plus 4 times z is equal to 0. And then same thing, subtracting over this term right here to the other side of the equation. Now we'll solve for y. So y equals negative 7 over 3k plus 4 times z. So if you look at what we just did here, we solved for x and y, and we have them defined in terms of z. So z is our free variable. all right? And we haven't run into any other issues that would keep us from finding a solution to this system. We have infinitely many, which is perfectly fine, but we just wanted to make sure the system is consistent. The only problem we had was early on, we had to assume or make the condition necessary that 3k plus 4 was different from 0. But otherwise, it looks like we're in good shape to have a solution to this system. Okay, so we can just summarize now and say we'll have infinitely many solutions as long as 3k plus 4 isn't 0, so as long as k does not equal negative 4/3, right? And so if we were to write an ordered triple x, y, z, it would have the following form. So x is equal to k minus 8 over 3k plus 4 times z. Y is equal to negative 7 over 3k plus 4 times z, and z is just z, right? That's the free variable. And you could write it that way, or as we've seen a couple times, you can just factor out this z from the ordered triple and then put it in the form. Let's just zoom in. K minus 8 over 3k plus 4, negative 7 over 3k plus 4. I'm just factoring out the z. 1, and then you write the z off to the side like this. Ooh, that's nice. Okay, so that concludes the lesson for section 1.2. Give the video a thumbs up if you found it helpful. Subscribe if you haven't already. And then we have plenty more linear algebra coming your way. Also, if you need help solving your homework exercises for Calc 1, 2, and 3, I'll link here my Patreon. There's lots of exclusive content on there, so make sure you sign up. Wishing you guys lots of success and talk to you soon.